Alright, hell yeah. This is so cool. So I made this problem, and that red is the vector, and we need to make it into two components. And you can just totally see one's parallel to the plane, the other is perpendicular to the plane. The take-home points for this problem is that if you find a vector perpendicular, it's considered a free vector. If I put it over here, it's the same direction, you know what I mean, and for whatever magnitude it is. Now this parallel one, this can trip you up, because hell yeah, that's parallel to the plane. So is this vector, that's also parallel. So if you're adding vectors, like hey, we're adding these two components, I start from here, add this, and then add this. So if I add a vector, let's say this direction, which is parallel to the plane, I'm going to go here, but then to get to this part of the vector, this is vector f, I would go from here to there, but then I would have to go at a wonky angle, you know what I mean, back up to that point. So sure, I can add any two vector components, one parallel to the plane, and still get to the top of this vector. But the question says, hey, I want a vector that's parallel and then perpendicular. So hell yeah. And this perpendicular component, it would be the same anywhere. But again, if we go from here to there, so from here parallel, and then just go straight perpendicular, well, we just made a vector that's over here. We're not even in the direction of vector f. So hell yeah. So let's take a look at how this problem kind of works. The problem states that we have a plane that's 2 inches, so that's what we have here. This is exactly 2. And then we have 6 inches. That's what this is. So I don't know how you see it, but this is the x-coordinate, this is the y-coordinate, and this is the z-coordinate. Now for this problem, it was really tricky because they have this force, you know, just kind of drawn arbitrarily, and I had to look this up because I was just like, well, doesn't this force have to go through the origin? And the answer is no, because I could have a force that's in this direction, and again, that's the take-home point for this problem, is this is a free vector. I could say this force acts over here. Now, it would change the dynamics if this was a rigid body, like hell yeah, it might want to rotate this way, compared to, you know, having this force be right through the center of mass, let's say, it doesn't cause rotation. But this is a free vector, so even though they have it drawn just from some arbitrary point that doesn't look like it goes through the origin at all, well hell yeah, I could have this force vector just right here. It don't go through the origin, but guess what? It's got the same direction. So sweet. Alright, so now let's dive into this, because this is literally probably one of the hardest problems for me. You know what I mean? I think this is the hardest problem in this book for me, and the reason is there's just so many ways to proceed, and it's really difficult to see how to get to the solution fast. So let's talk our way through it. We are going to take vectors a and c and a and b, you know what I mean, and then we're going to do the cross product, and when we do that, we're going to get a vector that's perpendicular to this plane. So that was the cool thing about making this three-dimensional, is that I can, when I get a vector that's perpendicular, I can just take this plane and then rotate it horizontal, you know what I mean? So now this pen represents that perpendicular vector. Cool. And guess what? This perpendicular vector is in the same direction as our perpendicular component. So when we do the cross product, we're also going to divide this. A cross product gives you a vector, so hell yeah, we just cross this with this, right-hand rule, we get this perpendicular component. It's going to have some sort of value, you know what I mean? But then we're going to divide it by its magnitude, and that's going to be the pure direction, you know what I mean? It's going to be the direction associated with the x, y, z coordinate system for a perpendicular component. So sweet, so we know that this vector will also have that same direction. Alright, hell yeah. So then the next aspect of it, we're going to take that horizontal vector after doing the cross product, and then we can see that the simplest thing to do, you can either do another cross product and find a magnitude. That's kind of a slippery slope that I would go down, but the simplest thing to do is just do a dot product between these. A dot product says, and again, this is a unit vector, and this has the magnitude, and this force is well defined. It's 20, 30, 50, I'm going to take a moment to say, like, how do you guesstimate the magnitude of this? Because in 2 dimensions, you just use Pythagorean's theorem. Well, and let's say in 2 dimensions, both of these terms were 50. That's the biggest this vector could be when both terms are at a 45. The components are the biggest. And that would be a square root 2. It would be 50 times square root 2. Square root 2 is 1.4. So at the most, it would be 50 times 1.5. You know what I mean? So it would be 75% had we just had 2 components. If you have 3 components and they're all equal to 50, it's going to be the square root of 3, which is 1.7. And so at most, if these are all 50, 50, 50, at most I'm going to get 1.7. That's going to be 50 plus a 10% tip would be 5, but multiplied by 70. Multiplied by 70, that's 35. That'd be 85. So at most, this vector could be 85. So right there, that's probably the most brilliant thing in this whole video besides welding this thing up. But hell yeah. And then if these are half of what this is, you know what I mean, we're talking, it's not going to be 1.7. It's going to be like 1.25. You know what I mean? It's going to be 50 plus like 25% tip. 10% tips, $5, so it's going to be 55, 66. So I'd say 65. You know what I mean? So that's just a really quick way to get an average right there. Alright, so we have this force vector. It's got a magnitude of 55. Coming back to our unit vector, we're going to dot, I think the simplest mentally way to go would be to dot this vector, which has a magnitude of 65, into this direction. And it's just the horizontal component. So you can see that this whole magnitude is 65. If we do the shadow, this distance, I don't know, maybe 50, you know what I mean, whatever. And so doing the dot product, guess what? That gives us this component, which is this perpendicular. So now we know the magnitude of this perpendicular component, and so we're just going to multiply that magnitude by the unit vector. And so we have every component of this vector, you know what I mean? So we now know F, and we now know the force in the perpendicular direction. Okay, hell yeah. So, you know what I mean? And this is where I would just go down a rabbit hole. I have. If I forget how to do this problem, I do as well. But the crazy thing is, like, I think the crazy thing about all this vector addition, subtraction, dot product, cross product, just all the manipulations you can do with vectors, is like forgetting about the Pythagorean theorem. It's like learning trigonometry and then forgetting about the Pythagorean theorem as an equation. So the same thing when it comes to adding vectors. If I'm saying that A plus B is equal to C, and I don't know A, but I know B and C, well, hell yeah. A plus B is equal to C is the same thing. If I want to find A, that's the same thing as C minus B. Okay, hell yeah. So literally it's that simple. I take this vector F, subtract it from the vector I just found, and that literally is these components. And that's wild as that. So hell yeah. So under 10 minutes, I'm going to try to do that answer as fast as possible. We're going to juice this baby out. Alright, hell yeah. We're going to go over the quick solution to this, and then we dive into all the little rabbit holes, and so stay tuned for that. Anyway, the solution to this is to take a cross product of 2 vectors along this plane. I just chose AC and AB, and we're going to do that cross product. But we need to know what vector AC is, and from a technical perspective, vector AC is vector OC minus OA. That's very technical. We explain that a little bit more, but I do that. And vector AB is vector OB minus vector OA. And so I will explain this. If you subtract a vector, it's the same thing as adding the opposite. So we're going to go OC plus, if this is OA, I'm going to add the opposite. Cool, I'm going to be out there. And so see how that vector is the same as this. It brings up the idea of free vectors and transferring them from one location to the other. Okay, hell yeah. Anyway, or it's just super simple. If I got AC crossed with AB, well, AC is the what? I got to go negative 2i 6j. So that spells it out. AB is negative 2i 5k. So What a technical nightmare just to do something that's fairly easy. But this does come in handy for complicated problems, especially dynamics. Got to do it. Anyway, so hell yeah. So we do this cross product. We're going to have A cross I cross K. That's going to be a negative. So we got negative 2 times 5 is going to be negative 10, but we got I cross K, that's negative J. So sweet. So we got the negative 10, we got positive 10J. Cool. We got I, that's it. J cross I is going to be, well, we got negative 12, but J cross I is negative K. So we get 12K. Cool. And then we got 6 times 5 is 30, and J cross K is a positive I. So well, we get this vector. Cool. And then we're going to figure out why that's useful. And then here's the denotation. This is the denotation of that vector. So if we just say AC cross AB, this is a vector. I can just leave it like this. I don't have to call it, you know what I mean? I could call it vector D and move on with life, but I keep it in this form. This is a vector, and this is what it is. Cool. I can also find the magnitude of it. We do that with the absolute value signs. So that's the square root of each of the components squared. You know, adding them together, there's going to be 900, 100, 144. So it's 1,000 and 144. Cool. Square root that. All right, so that's the magnitude of that. Okay, so now I have a vector direction. I know its magnitude. What we're going to do is get a unit vector. So we can divide these components by the magnitude. That gives us a unit vector. So this is how I could write that unit vector. I'm going to do the unit vector of this cross product, which is a vector. Cool. So the unit vector is going to be that vector that we get from the cross product divided by the magnitude of that vector we get by the cross product. So still, great ways to write these. Overly complex, you know what I mean? Where we could just say vector D divided by the magnitude of vector D if we just labeled that something. Cool. All right, so that's the unit vector. And for this problem, it's pretty cool because any vector that's perpendicular, you know what I mean, it's in the same direction. It's kind of a free vector. Don't matter where it is. And we kind of talk about that more in the... Anyway, so moving on, and we get this perpendicular vector. Well, sweet. Well, this is important because our component that is perpendicular, this is our vector component that's perpendicular, is going to be the magnitude, you know, of that component, just kind of multiplied by that unit vector that's perpendicular. So sweet. All right, so how do we find the magnitude of that perpendicular component? Well, we take the unit vector and we dot it with the force vector that we already know, or the force dotted with the unit vector, either way. But if you dot these two things together, this gives you the magnitude. You know what I mean? It's the horizontal component. If we dot this vector in with the unit vector in that direction, we get the horizontal component of this magnitude. And that is this perpendicular component. Hell yeah. So that's just 20i times the I term of this perp. And then we got 30 times that, and then we got 50 times that component of the perpendicular vector. Cool. And so we get a number. This is 44.3. And hell yeah. And then we just multiply this 44.3 times that, like we said, well, once we find the magnitude, we just multiply it by the unit vector. So yeah, 44.3 times the I component is the I component. And so we can find each component of the perpendicular vector. And at this point, it's just like you might be like, well, now where do we go? But never forget, you know, the simplest equations is like, hey, the vector that we're trying to find is just the addition of the components. So hell yeah. So if this is, so A plus B is equal to our vector, you know what I mean, F. And so if I already know F and I already know B, well then hell yeah. Vector F minus vector B is vector A. Cool. So we're going to find that parallel component, just rearranging this equation. So it's vector F minus vector perpendicular. We already have that. And so hell yeah, it's just the I component minus this component, the J's minus this, the K minus that. So that's what we have here, and we get that parallel component. We're done. You know what I mean? So that's cool. we can do a double check on reality. We can find the magnitude of this parallel component by taking its ijk components, squaring them, adding them, take the square root. That gives us the magnitude. So we got the magnitude there. And then, you know what I mean? So back to this. If we know the magnitude of this, the magnitude of this, and the magnitude of this, well, yeah, Pythagorean theorem said that this squared plus this squared has to equal that squared. So we do a little check on reality. That's what we have right here. We take this squared plus this squared. We get 3,800. And we take our magnitude of our force vector. I guess I didn't, you know what I mean, talk my way through that one. But the magnitude of this is the square root of 20 squared plus 30 squared plus 50 squared. And so that's that. So if we square that, we also get 3,800. So that's our check on reality. And hell yeah. So that's it. But yeah, this video can be a clinic, and I'll try to do more videos on this, because you could do every aspect of dot products, cross products, like things from this. Cool, we have this component and that component. You know what I mean? We can use tangent to find these angles since we already have them. But at certain points in the game, like, hey, we already, you know, we knew the magnitude of the force vector. It was 61. We knew that from the get-go. And so the second we found this perpendicular component, well, hell yeah, that gives us a ratio of perpendicular to hypotenuse. You know, however, or adjacent to hypotenuse or opposite to hypotenuse, doesn't really matter. But yeah, you can find both angles now, and so that's pretty cool. Or the second that I get this perpendicular component, same thing. Use Pythagorean's theorem, and I can find this. This squared minus this squared is equal to that squared. So right away, I could have got this term, you know, right when I solved for that term, but it's so surprising that I always forget the simplest equations, that, hey, two vectors add to your resultant. And usually that's what they're asking. They're like, hey, find the two components that add to the resultant. And so, sweet. All right, so now, you know what I mean, continue on, because we do this problem in depth. And I definitely go, I spend a lot of time on free vectors and how you can change their you know, location and why. How basically all cross products, dot products, vector addition, you can do as free vectors. They're whatever the word is. Who cares about where their locations were? You know what I mean? Like I mean, as long as they are where they are, you know. But it's the numbers, the quantities you get from them can most times be treated as free vectors. So those operations can be done kind of as an aside and then brought back into the problem where they're, you know, because even for this problem, it doesn't matter where this force vector. It's so surprising. You could really trick the students and put this force vector, you know what I mean, like right there. As long as you get you know, the direction on this is just so off. But just put the magnitude in a. But yeah, it's still the same problem. It's still really wild that this vector is a free vector for this problem. You know what I mean? If this was a rigid body, hell yeah, you put a force on it. It's definitely going to change its motion, that's for sure. But all right, thanks for joining me on this one, and hell yeah. All right, hell yeah. So welcome back, and now we just have this thing to stare at, and I'm going to try to do this in the fastest way possible. People are just like, hey, you know what I mean? Be less confusing. Okay, let's try that. So we need to take the cross product of AC and AB. And that just makes normal sense, because if we do that, we get a perpendicular that sticks out towards us. So hell yeah. And you know what I mean, we'll just do that. All right, but we need to know what AC is, and we need to know what AB is. And I'm going to do that. I'm going to do the MIT approach, because let's say you just didn't know that AC was just like, hey, I'm just going from A to C. How the hell do I get there? Well, -2, +6. -2i, +6. Cool. The other way to get there is make a vector O to A. So this is O to A, and this is tail to tip O to C. And this is kind of the definition of how to get to AC. Vector AC is, let's write this in. So vector AC is, so if we're going from A to C, okay, sweet, that's vector C minus vector A. So it's going to be vector O to C minus vector O to A. And I'm going to share this because, like, subtracting vectors isn't as obvious. So what we do is just do this. Say O to C plus, and then anytime I see a negative, do this. Negative 1 multiplied by O to A. So now we still know what O to A is, but we're going to take the opposite. I think taking a negative, turning it into a product is like, oh, now I see it. This is O to A. Oh, hell yeah, that's opposite. So this would be the opposite. This would be O to A, but times negative 1. Cool. And now we're just adding this to this. All right, I'm gonna take a step back. Let's say we just added OA and OC. Well, hell yeah, we're gonna go this way and then that way. You know what I mean? Vector addition, I think we're just groovy with. Everyone knows, and then here is the resultant vector. Okay, hell yeah. But now we're gonna do it with this negative. You know what I mean? We're gonna add OC, and then we're gonna add OA, but the opposite. So we're gonna go that way. So hell, we just did vector addition. OC plus the opposite of OA. So sweet. That's where we're at now. And does it make sense the other way? We're going to add OA but the opposite, and then add OC. So there's the parallelogram method. 2 ways to get to that same. Okay, hell yeah, I'm gonna kind of speed it up. Well, we got to see what this was. See how this vector is literally A to C. So this is what I learned. And check this out. Alright, hell yeah. So I had to learn this today. So AI is amazing. It was just like, well, when a vector can be moved around a plane without changing its magnitude and direction? That was my question. I was like, what the hell is that called? It's called a free vector. Sweet, we already explained that for a perpendicular. Okay, hell yeah. And then I wanted to know is just like, well, a vector is considered a free vector when it is only defined by its magnitude and direction. I mean, you can move it around. You didn't place it somewhere and that's going to cause a rotation about, rigid body. And then this was the nuts and bolts. I was just like, whoa. So can I treat any vector as a free vector to perform dot and cross products, to do the calculations, and then put that vector back in its original place? And hell yeah, you can. So that's exactly the fundamentals of what we just did. That is probably the coolest part about this video, because I never do this, and I hate subtraction. I've never understood the subtraction of vectors until I made this video right now. Anyway, so hell yeah. So what we just did was we just did a subtraction, and we get this vector, and you can see it's a free vector that's the same direction and magnitude as OA. So we did it. We found, I'm sorry, AC. Hell yeah, we wanted to know AC. We subtracted this from that, which was this plus the opposite of that. We got this vector. It's a free vector that has the same direction. All right, juicy. All right, so we're going to go a little faster. We're going to do vector AB. Can you do it? You know what I mean? Vector AB is going to be vector OB minus vector OA. Cool. I guess we're going to do it. So, hell yeah. That's going to be OB minus OA. Alright, hell yeah. So vector OB is 5k. So we got 5 in the k hat. Oh, I don't even think we actually solved for this one. Okay, well yeah, it's cool just to do another one. So we got 5 in the k hat plus, now what's OA? O to A is 2 in the I hat. So it's 2 I hat, but we have to do a negative 1. You know what I mean? Because this is OB plus OA times a negative 1. This is the opposite. I think adding that vector, but the opposite of it. That's very clear. Sweet. So now we have vector OB minus OA. So we did that. So it's negative 2i plus 5k. All right, that's vector AB. Let's go back to what AC was. AC was going to be, let's do it just kind of fast. OC was 6j, and then OA was 2i, but we have to add the opposite, so that's going to be negative 2i, 6j. Sweet, so we got negative 2i plus 6j. But man, that's hella technical when it's just like a quick double check is like, what the hell? A to C, we're going to go negative 2, positive 6. You know what I mean? And end of story. To get from A to B, hell yeah. We're going to go up 5. Or negative 2, up 5. Hell yeah. So there you go. So A to B. Damn it. A to B is that. A to C is this. Alright, now let's shake it out. So we have vector AC crossed with vector AB. That's what we're going to do. We're going to go AC crossed with vector AB. Sweet. I'm going to do it the fast way. If you've never done this before, you do I, J, K, and then put vector AC right here, which is negative 2, 6, and then 0. And then vector B on the next slot, that's going to be negative 2, 0, and 5. Now, I would draw two things. Draw your I, J, K axes. How you know you've drawn this right, always start in the X direction. And damn it, I need to make better videos because I missed the day they taught unit vectors. You know what I mean? You can call this I direction, but you can't call it I hat. I hat is a vector it's a vector in this direction. You can call this direction I. You can call this direction X. Typically you do X, Y, Z, but then you call this vector a vector in this direction, a unit vector in this direction, I hat. But again, you could call this direction I, you could call this direction J, and you could call this direction K. But you can't call this direction, I mean, you can't say that the direction is I hat. I hat is a vector. And I'm going to hopefully not have to explain that every time. I'll try to make a nice little video yeah, but I've made that mistake my entire life. You know what I mean? No one taught me unit vectors, I swear. Alright, hell yeah. But if you do, and I'm still going to say, hey, this is in the I direction, so who cares anyway? Okay, so we have a vector in the I direction, and we're going to cross it with the J direction. So we got I cross J, and hell yeah, we got positive K. So we know that these are all the positive, terms. If I switch these around, if this was, and I did I cross J, well, positive K would have to be down below. And you could do that, but, I mean, definitely I, J, K. This is probably the simplest way to do it. The other thing that I write is I, J, K, and I do it twice. I, J, K. So now when we cross things together, like what we're doing is we're like saying, hey, if this is a distance, r, and this is a force vector, and we're crossing them, they have a perpendicular distance, r cross f, this gives me a vector of like torque, you know what I mean? And how you would do that is like if I had, let's see, how could I do this? We're going to have a door this way. Here's the hinges. Here's the distance, so this is my r, and then there's my f. So we got r cross f, and hell yeah, we got a torque. This door's going to open. So there you go, r cross f. And you can only open a door if this is perpendicular. If you're just pulling this way in the direction of the door, ain't going to open. If you pull at a slight angle, well, hell yeah, it'll open a little bit, but it's just a percentage of that r times f. You know what I mean? So that's what a cross product is. I shouldn't be going into heavy detail on this, but I mean, if I'm going to set up like the quickest way to do this, and you're just doing this by guessing, oh hell no, you know what I mean? But this is the fastest way. So anyway, but if I do have something in the I direction and I cross it with the J, hey, it's totally perpendicular. So I can take this value of I, which is just 1. See, that's almost a better way to do. Draw your unit vectors, but put the value on them. So then this is going to be 1 times 1 is 1. Cool. You know what I mean? And then if this value, like this right here, is negative 2 multiplied by 1 times the unit vector. You know what I mean? So this is a vector, you know what I mean, in the negative x direction. And so, hell yeah. But I think you get it enough. And so if you're able to cross at a 90-degree angle, I into j, well, hell yeah, you're going to multiply those two numbers, you're going to get the full component. Now, if you do it the opposite way, j into I, well, that's going to be downward in the k direction, so we have to just kind of keep track of that. So if we go from I to j, j to k, so I cross j is going to be positive k. J cross k is positive I. K cross I is positive j. You know what I mean? And if you go the other direction, if I go I cross k, well, that's going to be negative j. Cool, so let's try it out. And this method is sweet because you can just cover up one of these and we're going to get the I components. So I'm going to get the I hat components and they're going to be this. And right now, like, you know, you would take this and we're crossing this top into the bottom. So you always have to start with the top. So we're going to be, I guess that doesn't really matter, but yeah, that actually doesn't matter. But anyway, this matters. Let's do even this one. 0 times 0. But this is k cross j. What the hell would have that been? K cross j would have given me negative I. So I'd be 0 times 0, but I got to put a negative on it. So now this way is j cross k. J cross k, that's in the positive direction. So that's going to be positive I. So sweet. So I'm going to get 30i. And then I'm just going to get one term there. Sweet. So I got 30i. Put my fingers over j. And then I'm going to have I cross k. Well, I cross k is going to give me a negative. So, and right here, this isn't typically the way that they would do it. You would typically go this way. You'd go over here to here minus here to here. Well, why would you do that? Because, no you wouldn't. You would go this way. Sorry about that. You're going to go this way. You're going to go in the positive. Start here, go in the positive direction. J cross k, hell yeah, I'm going in the positive direction. We just said j cross k is positive I. So even though you're going this way, think of it more as going this way. J cross k. So your j cross k is positive I. And then k cross j is going to be negative I. So that's why they do 6 times 5 minus 0 times 0. A better way to do it would be 6 times 5 plus 0 times 0 multiplied by a negative 1. And so, alright, hell yeah. Alright, now I don't mind doing a longer video because this is the stuff where it's like you want to learn this more than just get the answer. Like while you're doing these problems, you want to get hella better at this type of stuff. So, sweet. So we just did it. J cross k is 30i. So now we put our finger on, and let's go over to k, because k is going to be the same thing. I cross j is a positive, minus j cross I. Because if I go j to I, that's going to be negative k. And so that's why they go negative 2 times 0 minus 6 times negative 2. But let's do it the opposite. Let's say it's, we're going to go I cross j, so it's going to be negative 2 times 0. Cool. And that's going to be a positive k. And then let's say 6 times negative 2, and we're going to add it. We're going to do negative 2 times 0 plus 6 times negative 2, but j cross I is in the negative direction, so we're going to multiply that by a negative. So it would be negative 2 times 0 plus 6 times negative 2, but j cross I is negative k. So put the negative 1, and then, you know, we're finding the k terms here. All right, so hell yeah. So let's go back to how you would just do it. So we have the I term. 6 times 5 is 30. Cool. The j term. The j term is the more complicated one because I cross k, if I go this direction, well, hell, that's the opposite way. I cross k is a negative j. So I can go negative 2 times 5. I can do this one first. But in the books, they're going to be like, well, do this. Go here to here minus here to here. But, like, why memorize that? You know, instead of just being like, hey, I want to go any way that I want. So I want the j components. I'm going to go I cross k. I know that's going to be a negative. So negative 2 times 5 is negative 10 times negative 1 is 10. So this is going to give me a 10j. And then this is multiplied by a 0. So I'm going to get 10j. And stuff like this I looked up. What you can't do is you can't, you probably can't do that. But anyway, you probably got to put this out in front. No, I mean, it would just be like this. But yeah, you need some sort of scalar in front of, your vector. You know what I mean? You can't just have an I hat. I guess it's implied that it's 1, but it's good to put that in. Okay, I'm sorry I'm putting the value out in that direction of the k. But anyway, put your finger over k. We're going to go I cross j. I cross j is going to be positive k, but it's going to be negative 0 anyway. And then we're going to go, that's why they do minus 6. We're going to do minus 6 times negative 2. Why? Because j cross I is going to be negative k. So 6 times negative 2 is negative 12, but we have a minus of that, so we get positive 12. Holy hell, that was difficult to explain, but I think I did a pretty good job of being like, hell yeah. I cross j is positive. Positive, j cross I is negative. So we're going to multiply these, but I'm going to gotta multiply by a negative 1. Cool. Alright, so now we have this vector. And, whew, that was brutal. So that is this vector. We have 30, 10, and 12. And I'm going to say it's the cross product of AC. Sorry. So this vector is AC cross AB. Now, we know a cross product is a vector, so I can just write it like that. And I can say this is equal to 30i plus 10j plus 12k. But we want the unit vector, because back to our problem, we know that this perpendicular is in the same direction as the perpendicular component. So how to turn this cross product into a unit vector is to divide by the magnitude. So I'm going to divide all 3 terms by the square root of the terms squared and added. So 30 squared plus 10 squared plus 12 squared. Sweet. We're going to have 900 plus 100, that's 1,000, plus 144. So that's going to be the square root of 1,144. Alright, hell yeah. I'm just going to plug this into our calculator. So I'm going to say, I'm going to do square root 1144, store it as x. I'm going to go 30 divided by x. I'm going to store that as alpha a. I'm going to go 10 divided by x, stored as alpha b. 12 divided by x, stored as alpha c. Alright, so now we have our unit vector, a, b, c. And so this is 0.89i plus 0.30j plus 0.35k. And if I square each of these and add them and take the square root, it's going to have a magnitude of 1. That's how I would find the magnitude of this thing, just by squaring each term, adding them, and taking the square root. So let's do that. Square root alpha a squared plus alpha b squared plus alpha c squared. Alright, sweet, we get what? Alright, so now we know we did a check on reality, we have a unit vector. Now we're going to say, hey, my force vector is something like this. My unit vector is perpendicular to the plane. And I'm just going to now call this the unit vector, perpendicular. So hell yeah. So this is unit vector perpendicular, has a magnitude of 1. Here's our force vector, and it's 20i, 30j, 50k. When we do the dot product, the magnitude of this, that's what we're basically going to yield. This has a magnitude, and we should just figure out what the magnitude is. It's the square root of 20 squared plus 30 squared plus 50 squared. Yeah, hell yeah, the magnitude is 61.6. So we were pretty close with 65 or whatever we said. Alright, sweet. So when we do the dot product, we're going to do f dot the unit vector perpendicular. And you could do the opposite. It's the same. Like this kind of visually makes sense, where the opposite, this has a magnitude of 1, and this has a magnitude of 61.6. So doing the dot product, you're still multiplying numbers, but only if these vectors are in the same direction do you get to multiply 100%. If they're perpendicular, you can multiply the numbers, but you got to multiply by 0. You know what I mean? So a dot product is only the component of this that's in this direction, and then that number multiplied by this. And if this is 1, hell yeah, the dot product just gives you that component. So that literally will be the magnitude of this. That's all it gives you, though. dot product is just a scale. It's just a number. It's just a magnitude. But we already know that the perpendicular component, the unit vector perpendicular, is the same direction as this perpendicular component. So once we find this scalar, it's kind of bizarre. We just instantly take that scalar and then just multiply it as a number up against the unit vector. And that foils through the I, j, and k terms, and this yields us the perpendicular component of the force. And again, just foreshadow, then we know that the force is equal to the perpendicular component plus the parallel component. We know what the force is. We know now what the perpendicular component is, so we can find the force parallel just by the total force minus the perpendicular force. All right, so hell yeah, let's juice this out. So the dot product is taking this 20. I'm going to say this is A, B, and C because that's what I have in my calculator. So we're going to do 20A plus 30B plus 50C. So again, dot product is just the component in the I direction multiplied by the component in the I direction. And let's slow it down and see how that works out. All right, I was thinking because these have x, y, and z components, like our force here has a x component, a y component, and a z component. That's what this is. And then our perpendicular vector has an x component, a j component, and a k component. And just visually, I can't. I would have to do another. That's where my mental game kind of breaks down of explaining that. But when we get it like this, hell yeah, you can just see that. Yeah, what we have right here is, yeah, we know that this is the plane and this is the force vector. Sure, it has 3 components, but we found a perpendicular vector, and we can see that those, as long as we get them flat, in a 2D plane like that, oh hell yeah, we can totally see that this force dotted with this force gives us that horizontal component, and that's going to be this perpendicular component. So, all right, booyah. So here is the angle between them is kind of the dot product, and then we have this horizontal component. So this height is going to be the dot product. But I apologize, I don't have a 3-dimensional model to show you how, because that's important. Just like we did the cross product, you know what I mean? We had a component in the I and we crossed it into the j. And then so that gives us a component in the k. It gives us, multiplying those two values gives us, the I cross j part for sure gives us that component in the k, but multiplying the values gives us the magnitude of that. So cross product is still the multiplication of two numbers. All right, sweet. And so, yeah, I'm gonna explain that because that's important. I need to get better at that, explaining the dot product. People usually don't spend too much time on the dot product. They just say, hey, multiply the two numbers, multiply the x terms together and add the, multiply the x terms and then add them to the multiplication of the y terms and then add them to the multiplication of the z terms. But if you can't see physically in 3-dimensional space what's going on there, it's just kind of hand waving. So let's slow it down. Alright, hell yeah. And I think this is kind of where I really enjoy this stuff of just like, hey, like I know how to get to point A to point B. Like I know how to explain this subject, but this is kind of just the first time ever doing this. So like what do we have? Let's write this out. So we have a force vector, and we're going to dot it with the perpendicular. And so the force vector is 20I plus 30j plus 50k, sorry about that. And we're going to dot it with our unit vector. And I like to do unit vectors as decimals. Don't get too crazy. At least do 2 places. You know what I mean? You could do one. You could do 3. You could do 1, but 2 kind of represents it pretty well. So this unit vector perpendicular is going to be 0.89 I plus 30j plus 0.35k. And so now we're going to draw this in 3-dimensional space. Like this is the whole reason I kind of made this model. because like if you can see something in three-dimensional space, you're just like, oh hell yeah. But we can still do so, and I apologize. I'm still just going to call these. Now I could get better and actually put arrows on this, but I have no idea. I'm just really bad at saying this is the I direction. AI said it's fine. You can call this the I hat direction, but it represents a unit vector in the I hat direction. Like you're better off saying this is the I direction, but no one, it's the X direction. It's the X direction represented by a unit vector I hat. You know what I mean? I don't know. Like, for the life of me, I feel like that's why I graduated without knowing what the hell a unit vector was. Just because it's... You might as... I don't know. You might as well just call this X hat. Yeah, why not call this Y hat? But anyway, this is the Y direction, Z direction, X direction. Here's our unit vectors. They're unit of 1. But now that I just even drew 1, I put a scale on it, which I didn't want to do. So anyway... Alright, so let's write in these. So this... I don't know. This is where you would just want to do, hey, this is 0.9, this is 0.3, this is, or you know what I mean, this is 9, this is 3, this is 3.5. You know what I mean? Because this helps you get the direction. So we're going to go 9 in the X, we're going to go 3 in the Y, and then 3.5. So there you go. So this is that unit vector perpendicular. Let's do this one. It's going to be 2. And I'm not doing anything to scale. I'm just going, hey, if I'm going this way, 2, I better go this way about 3, and this way about 5. Call it good. All right, and hell yeah. So this is F. And I don't know. It's really difficult for me to see that there's not a 90-degree angle right here. But let's try this again. We're going to go... you know what I mean, 9 this way, 3 this way, and then 3.5 up. So that's how we got to here. This one is going to be 2, 3, and 5. So again, let's bust out this. Because for this one, like this is our force vector. It's going to be from the origin, and it's going to be, you know, up here. Now the perpendicular from here is going to be over 9, over 3, and then up 3.5. So there you go. So even just visually right there, now you could see that, hey, that's the angle between these. But it's just really difficult to see on paper. So we got about a 45-degree angle. So, but that's where I'm going to try different methods to get these, to do this faster. I think welding's a pretty good method. And it would be good for students to like have a welding lab where you're just like, hey, like you have to weld your... But man, it's really difficult to weld very thin metal. It takes a lot of skill because you have to control the heat. You have to kind of ball it up, like ball it up and then aim the heat at the ball, else the metal just like breaks in two. Anyway, all right. So hell yeah, so we're almost there. So this has a component this way, and then up. I should probably draw this a little bit better. This one has a component of 2. You know what I mean? It's got a component this way, and then up. So all 3 of these things have 3 components. So let's draw this. Man, let's draw this one more time. All right, I promise this will be good though. And maybe we can make our axis. Just, I don't know. Like, yeah, this is where you might want to change your axis around so your problem kind of visually is better represented. But let's try this again. So we have X, or just, I'm just going to call it I, J, and K. Okay, sweet. And, yeah, so let's do this. We're going to go, I'm going to go 1, 2, and then 1, 2, 3, and then 1, 2, 3, 4, 5. So hell yeah. So this vector is F, and it's into the page. It's out at you. You know what I mean? We're going 2 this way, 3 this way, and then up. You know what I mean? So it's out at you. It's in this first quadrant. All right, now this one, I'll try to do just like, hey, 0.89, and then 0.3, and then 0.35. Yeah, it kind of runs into there. So I'm going to just not do it to scale, but I'm going to go this way. Yeah, perfect. I'm going to go this way, and this way. So there you go. So this has a component that way, a component that way, and a component that way. So this is our vector perpendicular. And this is the hardest part about doing statics with vectors and cross products, is because it's very difficult to see the components in a 2D space. But now we can see, hey, we have an I component, we have a J component, and we have a K component. And we have magnitudes of these, see? Same thing here. I have to get up to there, I have a I component, a J component. So this is going to be my I component for that one, J component, and we have a K component. All right, hell yeah. And again, these are free vectors. You know what I mean? So I can put the K component. So yeah, let's do this again. So we're going to do 3 little vectors here. Or three quad, what is this? Three coordinate systems. And then so let's do the I component. So I can say, hey, this I component, yeah, what's the one to here? They're about I kind of drew them about the same. But hell yeah, so there's one, and then here's another one just kind of laid next to it. Cool. So, and let's get values on these. So this one's going to be 0.89, and this one's going to be 20. So I have 0.89 and then 20. Cool. And then in the J direction, I'm going to have one that's 30, and then this one is 0.30J. And in the K direction, I'm going to have one that's 50K, and then this is 0.35. So I have another one, sorry, so this one is 0.3, this one is 0.35K. Now the whole deal with dot product is if you have 2 vectors going the same direction, you just multiply these 2 numbers together. So this is where, this is the I directions, this is the J directions, this is the K direction. And so this kind of visually shows that, hell yeah, I just get to multiply these 2 numbers together. But now this doesn't show you the full picture. I think it shows you that component, but we are gonna I'm gonna slow down just a little bit. Give me a sec. All right, hell yeah. So So what do we have? We have that force vector dotted with the perpendicular. And, you know what I mean? We have 20, 30, 50. So we kind of have this down 20, 30, 50, I, J, K, dotted with, I'm just going to kind of simplify this. We got 0.9, 0.3, and 0.35. That's kind of fully simplified. And this is very helpful because you're just like, okay. And then, so here's where you should not forget that dotting and crossing is still a multiplication. And treat it like foiling. You know what I mean? I'm still multiplying this by this and then adding it to the multiplication of this. So we're gonna go through that whole process because, you know, they'll do it once in a textbook, but it gets so redundant that you're just like, oh, but the second you go through that redundancy, you're like, oh, I get it. You know what I mean? Because we still have a multiplication. Like we're still doing, yes, this is still, check this out. So it's 20 times 0.9, but then it's I dotted with I. So there you go. Or this can be written as 20I dotted with 0.9I. Cool. And then moving on to the next term. Then we have plus 20.3, and then we have I dot J. which is the same thing as 20I dotted with 0.3j. Cool. And so in the textbooks, they'll probably skip this stage and just go to this. But, I mean, this is the foiling process. So we have the next term is going to be 20I dotted with 0.35k. So these are individual dot products. You know what I mean? That's literally spells out why we take a vector and break it up into 3 components. Well, what you just did there is now you have 3 different vectors. And so, like right here, this is 3, this will help me for other videos, because this really shows you the, like this, what this is I forget whether it's associative, but it's that, whatever, commutative, associative, I don't know the words, or I might be, but it's that process. It's the same, like this literally is 3 different vectors, and to do the dot product between this, represented as 3 vectors, you have to go through this foiling process. But what happens in that foiling process is, hell yeah, this is 20I dotted with 0.9I. So back to this is 20I dotted with 0.9I. 2 vectors in the same direction. We literally get to multiply these. It's going to be 100% of the multiplication of these 2 numbers. But let's say we come here and we got 20I dotted with 0.3j. So we have this 20I, but we're going to dot it with this 0.3j. So this is where you would, you know, put these all on on the same coordinate system. You would have your 2 components in your I direction. You would have your 2 components in your j direction, and you would have your 2 components in your k direction. And what we're just doing right now is we're doing this 20I dotted with 0.3j. Well, there's a 90-degree angle between these. So the shadow, and let's talk about that, because this also gets underlooked. If here's my vector in a 2D space, let's do this one. Like hell yeah, I can dot these 2 together, because I can do the shadow of this one. And what happens is, it's when you're doing the dot product, this isn't the number that you're getting. The only way that this is the number you're getting is if one of these has a magnitude of 1. If this has a magnitude of 1, hell yeah, this is probably less than 1. And if this has a magnitude of 1, then this is more than 1. So, and both, how I said that, both would yield a different number, but that's the only way where if one of these is a magnitude, if one of these is a unit vector, the dot product will give you the component of the vector with a non-unit magnitude. You know what I mean? So, all right. But else, if these are, you know, again, the dot product is still like, hey, this component gets multiplied by this component. So you're still multiplying 2 numbers, but you aren't multiplying, you know what I mean, this full magnitude times this full magnitude. Cool. So that's kind of breaking it down. So if I just said, hey, let's just take this component and, I'm sorry, we're doing the dot product. No, I just got confused for a second. But yeah, we have this vector dotted with this vector. Well, hey, let's just break this one into 2 components. One that way and then one this way. And literally, all we're doing is taking this dotted with this. We're multiplying these 2 numbers together. Like this one, this distance is irrelevant to the dot product. Cool. And if we actually dot this component with that, we get no, it's 0. You know what I mean? So we still have 2 vectors. So even though we have this, we're dotting this vector with this, like this vector for sure has 2 components. So that's the same thing as just, hey, dotting the vector that's parallel first, this number times that number gives us like basically the scalar of that. But because this is perpendicular, maybe this is in the j hat direction, this is the I hat direction, and j dot I yields 0. We can multiply these two numbers all day long, but we got to multiply it by 0 or 0% because it's just the nature of what a dot product represents. And that's where, I think it's very useful. It's like a shopping cart. It's like, I was just like, well, damn it, I got to come up with one good example of the dot product. I'm going to push down with a force, but I want this shopping cart to go. So I'm going to take a vector in this direction. It's a direction vector. It's a vector r. And so I'm going to dot f dot r. And what that's going to give me is and I'm going to take a unit vector r. So we got r as a unit vector in that direction. So sweet. So let's say this direction, I'm just going to measure it from here to here, is like 36 inches. And so I'm going to take that direction. Let's say this is the I direction. So I have 36I. It's the only component. I'm going to divide by the magnitude. Hell yeah. So now I'm going to say, hey, this is the vector, has a unit magnitude of 1 in the direction of this I direction. If I multiplied by the scalar, represents this distance. But if I divide by its magnitude, it just represents a vector in that direction with the magnitude of 1, which is now useful to me. Even though I'm kind of apples and oranges here with a force and distance. Like if I'm just representing this as this direction, so I'm going to dot these two together. So this kind of shows that hell yeah, this kind of represents dotting this with this only the horizontal. And how do you do this? Well, I would treat this as a free vector, do tail to tail. So here's my unit vector in the r direction. Here's my force vector, and hell yeah. So here now is my angle between them, and I can see that the horizontal or the cosine so like the sun is shining. This is the sine component that would indicate the magnitude of the cross product, but this is the horizontal distance. This is the dot product. And that dot product represents the actual juice, the force, being useful when pushing a shopping cart. That's going to be F equals ma, and you're going to get some change in velocity. Hell yeah. Alright, so that totally sucked, but no one's going to go over that of like why I dot j is 0. You know what I mean? And so you can foil this whole thing through. So we got 20.9 I dot I, and then we got 20.3 I dot j, 20.35 I dot k, and then just continue on 30.9 j dot I plus 30.3 j dot j. Okay, that'll jive. The I dot I is the only one that jives. Everything else is 0, 0, 0. And so you can see, but what a painful process. But it's good to do this every once in a while. J dot k, and then we got 50.9 k dot I. And so now that we went over kind of what it looked like, now when you do this, you can kind of visualize that in your head. You're like, oh, I didn't realize that this was 3 different vectors, like all yep, and cool. And I would have to let's finish and then talk about that. So we got 50.3 k dot j, and then we got 50.35 k dot k. Sweet. So that juices. So we got 3 components that actually matter. And that's why the cross product is way more beneficial to explain this, because I cross I is 0, but the other 2 terms, I cross j and I cross k, do yield. You know what I mean? I cross j, we just said was positive k. I cross k is going to be negative because it goes the opposite direction. No. I goes, yeah, it goes IJK. So I cross K is going to be positive J. All right, hell yeah. And you should always do that visually too. IJK. So if I had I cross K, yeah, because something was up with that. I cross K. No, hell no. It goes IJK, IJK. So it's just cool to have like two things in your wheelhouse to check your errors. So if I do I cross K, I can just, hey, put my fingers in I and then cross them into K, and my thumb is in the negative J direction. Or I can come up here, IJK, IJK. So if I'm going I to K, I'm going in that negative direction. All right, sweet. But yeah, with the cross product, you got two values that juice. Where if you do the dot product, that's why like there's no point to write all that out. You should write it out once just to see that, yeah, it still is a multiplication of two numbers. And hell yeah, I'm just going to double down on that point because it's literally like saying, well, let's say I do have 20i. That's a vector. Cool. And I'm going to dot it with 0.9i. Cool. But I should also dot it 20i with 0.3j. You know what I mean? And these are all individual vectors. So if I want to figure out, you know, the dot product between three vectors dotted with three other vectors, you have all these combinations. And so, yep, so that's where you get all of these 9 terms, but only 3 are directionally significant. You know what I mean? Only, back to the shopping cart, only the force that's in the direction that you're analyzing motion, you know, for this problem would be the only force you'd be interested in. You might be interested in like how much you're just pushing against the earth, you know what I mean? You'd be like, hey, you're just digging in to our freshly waxed floors, you know what I mean? Hey, push your cart more horizontal. That's what I say when I'm at the grocery store. All right, so that was useful because we already showed how cool this thing was, and then we showed you, I actually did a pretty good job of like explaining the answer. You know, I mean, now we're just lost down this rabbit hole of dotting, but I swear the dot product, even though it yields a scalar, you're like, what the, like, what does it represent? You know what I mean? And it doesn't, and it like literally is the biggest mistake. Dotting this with this does not just represent the magnitude. Like if this has a magnitude of 10 and this has a magnitude of 61.6, dotting these two together, you would get 601.6 times a percentage. And if this is a 45-degree angle, it's about 0.7. You know what I mean? So in that case, I mean, sorry, and I wrote it wrong. 600, you would get 61.6 times 10 would be 616 times a percentage. You know what I mean? So you're still multiplying two numbers. That's where a dot product is only a component of that vector you're trying to like figure out if you're dotting it with a unit vector. But it's real simple to do a unit vector. You just divide by the magnitude of that vector. So hell yeah. So that's what we're doing. And we're getting, what are we getting? That vertical component. And so, booyah, let's do it. So, you know what I mean? Yeah, super simple. Here's our two vectors, and we're going to have 20.89 plus 30.3 plus 50.35. And this is where I got to get better at guesstimating. This looks about 20, maybe 18. And how do you tell? You know what I mean? Hey, this is 90%. What would be 90% of 10? That would be 9. So what would be, you know what I mean? What would be 90% of 20? 18. So sweet, I got 18 there. 3 times 3 is about 1. And so, hell yeah, I have about 10. I have about a third of 10. So there are a couple ways to just do kind of guesstimations on the fly. Let's say this is half. No. I don't know how to do this one. I don't know what 50 times point. I do know what 100 times 0.35 is. That's going to be 35. But we're going to have half of that, so it's going to be 15, 17.5. Okay, so hell yeah. And I know that 8 and a 7 is like a 15. But I'm going to have 30. I'm going to have 45. Hell yeah. So I think it's 45. That's a pretty good guess. In our calculator, we got 20 alpha A plus 30 alpha B plus 50 alpha C. And we get 44.3. So it's always good to, you know what I mean, use your guessing skills. And 44.3. Now here in the problem, this is crucial information in two different ways. It gives us this magnitude. Gives us the magnitude of this perpendicular component. But it also gives us another piece of information. We just did the dot product. And I should have another visual where this, this perpendicular, this pink component, comes straight out from here. Because what did we just do? We just put this perpendicular component and we dotted this with that. Okay, so the angle between them was representative of the, and we did it with a unit vector. It wouldn't matter anyway. Let's say this was 60 and this was 10, and then we get that value of, it wasn't 600, it was like a percentage of that, about 70%, so that was going to give us 400, but we still know the magnitude of this, damn it, I said that wrong. So let's talk about that. So if this was 60, 1.6, and this was 10, I multiply the two numbers together, that gives me 616. How the dot product works, it's only a percentage that's important. If it's this, it's 100%. If it's perpendicular, it's 0. If it's about 45, it's like, 0.707. 70%. Sweet. So, hell yes. About 70% is 600. I don't know. I'm just guessing. 450. 400, 450. And so what can I do with that number now that I got the dot product? Well, I can divide it by that 616. So it doesn't even matter that 1 is a unit vector, and I think that can be the most useful piece of information. If I'm doing a dot product, cool, I'm taking this dotted with that. It's still this vector multiplied by that vector. You know what I mean? The most it could be is the magnitudes multiplied. But I know it's going to be a component less. And so what I do is I take that scalar and divide it by the magnitude had these been, parallel. Just the multiplication of the magnitude of those two numbers. That ratio between like what we actually get and the total magnitude is the same proportion as if this is a unit vector, then and this is 61. The component in this direction is 41. So 40 or 44. So 44 divided by 61 is a ratio of, and it is the same ratio of, and we have this angle, and so that's the cosine component. If this is the angle, the sun is shining, this is the sine component, this is the cosine component. And that's literally just kind of what I forget all the time. And anytime you do a dot product, it doesn't have to be a unit vector, right? You get a scalar, divide by the magnitude of those two vectors multiplied together, and then you get the ratio of it's a ratio of this triangle. It's the ratio of this side of the triangle to the hypotenuse. Cool. So even right now, we can know the angle, and what angle would that be? So that's and it's kind of tricky when you have free vectors, because we put the unit vector here and we got the angle between. So by Zorro, we have two perpendicular lines, and I use this little Zorro thing for trigonometry. I don't know. I don't think anyone else calls it Zorro, but hell yeah. So this angle is the same as that angle. You know what I mean? So so this is the angle that we just found. And it's, the ratio of it. So the inverse cosine of that ratio is that angle, so let's do it. So we have, I need to store the magnitude of that. So square root 20 squared plus 30 squared plus 50 squared. This is the magnitude of our force vector. I'm going to store that as alpha f. And we have 44. 44, I'm going to store that as alpha g. And so we have alpha g divided by alpha f, and we take the inverse cosine of that, and we get 43.9 degrees. That's why this problem sucked, because, like, hey, this angle right here was just, I couldn't tell if it was less than 45 or greater than 45. So we got 43.99. And don't quote me on this. The answer is not in the back of the book on this one. So if I make small errors, you'll just have to bear that out. All right, so we're not on a roll, But we're going through the stuff that I wanted to go through. You know, I just want to get better. And, yep. I guess there's a little bit of a sufferfest to some of my videos. But I think we go over some pretty cool stuff. So, I guess I go over the things that I think other people aren't going over, though. It's just like, so I'm going to take the time to do that. Sweet. So we have that angle and we got that component. And this is the wild thing of this problem, of this whole problem, is, oh, well, let's see. It's still not over, because now we know the magnitude of this component, but we know the unit vector, and we've spelled that out. It's like 0.9, 0.3, 0.35. So you have those three components, I, J, K. And so this perpendicular, so force perpendicular is going to be 20, is going to be the magnitude of F times that the unit vector in that direction. So we have 20 times 0.9, 30 times 0.3, and 50 times 0.35. And those are going to be the components. So hell yeah, let's do that. So alpha A, alpha B, and alpha C were our perpendicular components. We're going to go 20 alpha A. Oh, whoa. Sorry about this. No, I said something so stupid. Okay, so the magnitude, we found the magnitude of the perpendicular. So the vector that's perpendicular, this vector is going to be the magnitude of that, which is a scalar. This is a scalar, and we're just going to multiply it by the unit vector perpendicular. So my apologies. And this is this term is 44.3. So we're taking 44.3 and multiplying by that unit vector 3 times. And when we do so, it's fascinating. We still, because the squares of each of these add up to 1, multiplying it by a scalar doesn't change that. And that's tripping me out right now. So we take that 44.3, multiplied by our unit vector. I'm going to now store this as alpha I, alpha B, alpha J, stored as alpha J, alpha C, alpha G, stored as alpha K. So we have alpha I, alpha J, and alpha K. So doing this multiplication, we get 39, 13, and about 16. And sweet, if we take these and do the, if we take the square root and then square and add the terms, square the terms, add the terms, take the square root, we get the magnitude of that. So we get, and it's a good check on reality just to do. Hell yeah, that we just make sure we get the same term. Cool, so this is where I kind of fell into the trap that I know the magnitude of this one. Now I know the magnitude of this one. Why don't I find the magnitude of this one right now? Well, that's the longer way around, because it's sometimes the simplest equations are the hardest ones to see. Is that, again, we have this vector F. To get there, from here to there, is this component this way. It's vector A plus vector B is equal to vector C. Sweet. So, yep, and that's a really easy equation to mess up or just miss. So we have the perpendicular component plus the parallel component. So if I want to solve for the parallel component, I just take this and subtract this to the other side. And obviously it's going to be a negative. So we're going to have the force minus the perpendicular component. Sweet. So we have 20I, and then you know what I mean? We're just going to take the I terms and subtract them, take the J terms and subtract them, and take the K terms. So alpha I, alpha J, and alpha K. So I'm going to do 20, this 20 minus alpha I, which is 20 minus 39. And so I do get a negative. And then I'm going to go 30 minus alpha J. And then I'm going to go 50 minus alpha K. Because this is, I have 3 components here. We stored them in our calculator, I, J, K. And then I know these 3 components. Cool. And I'm going to store that as, and then so I have alpha N, alpha O, and alpha p in my calculator. So hell yeah. So parallel components are going to be negative 19, 17, 34. And then we just need to do a double check on reality. Well, right now we're done. We found the two. Alright, so we found the two components. Sorry about that. Ran out of juice. So yeah, we could be done just right now, but we need to double check that these are right. So one double check is like, hey, we have the three components of this vector. And the reason there's three, I mean, it's so fascinating that you can just put it this way, and you're just like, well, I could put it in plane. It looks like there's only one component. It's like that way. Well, it's because our vector, this is the x direction, y direction, and k direction. So if I actually start here, I'm going definitely in the x direction, definitely in the y direction, and well, which one are we doing? We're doing like the yellow one. So yeah, so I'm going actually in the negative x. So let's go in the y direction first. I'm going in the k direction and then in the negative x direction without going through this plane. Yep, I'm going this way, and that way. And is that what we find? That we have a negative I component, a positive j component, and a pretty big positive k component. Well, hell yeah, negative I, positive j, and a pretty big positive k. So there's a double check on reality. That is where something like this is just super useful, because every step of the way you can kind of better check your answers. But the take-home point is that the magnitude of this vector squared plus the magnitude of this vector squared, square root, basically the Pythagorean theorem. I know the magnitude of this. We already found the magnitude of that. We found the three components of this one. We better check its magnitude and just make sure Pythagorean's theorem checks out. So I have this as NOP, so I'm going to do the square root of alpha n squared plus alpha O squared plus alpha p squared. And I hope I come up with an error. I mean, I don't, actually. We're going to store this as, well, let's look, it's 42. 42.8. I'm going to store this as alpha h. So even right now, we have that. So it's just like, I never do this step, but we just found the magnitude of this, and we know what the magnitude of the force is. Force is 61.6. So again, we know the magnitude. So we can do this. We can put, well, we can either let's, two ways to do it. Well, holy Toledo. I want to find this angle. Yes. Oh, and you know what? I mean, I already know that this angle is 90 minus that angle. So if I go 90 minus, that's one check on reality. It's 47. 47. Yeah, so I think I did make an error. So we'll have to double check, but that's fine. I don't mind making this a hell of a long video. So yes, I think I have an error because this angle is not complementary to that angle. Oh, what the hell? No, sorry. No, we're good. That's why I didn't like this problem, because the angles are about 45 and the magnitude of these. So we already, alpha G has a magnitude of 44 and an angle associated of 43.9. So this problem is the worst for having components that are similar. I just made that mistake. This magnitude is 42.8. So before we get run away, and that's stored as alpha h, I'm going to divide that by alpha f. So now we have a ratio of 0.69, and that's going to be this magnitude to the hypotenuse. Another way to do this is be like, hey, this is close to 7, so why not do this? 1, 2, 3, 4, 5, 6, 7, and then do a magnitude of 1. And then do 1, 2, 3. I'm going to pull out. This is probably the way to do this, is to do this, draw a perpendicular line, you know, just renegade trigonometry. There's the angle. You know what I mean? So that is a good technique too, because you get this ratio, and I think people lose their friggin' minds. Anytime that you have a ratio where you're going to do like an inverse cosine of that, and that's what it would be. You know what I mean? We have, I want to find this angle, and I know the adjacent. do the sun is shining, this would be the sine component, so this must be the cosine component. But yeah, I know the ratio is 0.69. So the first thing to do is do 0.69 divided by 1. If this is a ratio, turn it into a ratio, because the inverse cosine, and what the hell does this say? This says the angle of a triangle that makes this ratio, where this is about a 7 to 10. Yeah, I said 7 to 1, but no, this is 10 and this is 7. You know, you can kind of get it. So whatever angle that makes, you know what I mean, that's what's up. And if this is 7, well, what do we know about triangles? Yeah, I know that this is 7.07. This is a 45-degree triangle. If this is less, what happens there? And it's not intuitive, you know what I mean? If this is a 45-degree triangle and this is 0.7 and this is 1, and I make this less, well, look at that angle. It actually increases. So I should expect an angle greater than 45. So hell yeah. So, you know, inverse cosine of that, and we get 46.007. And hell yeah. And 90 minus that, that's going to be 43.99, and that's what we had over there. So this is what I love about this problem, because it's such a, I don't know what, you know, whatever word you thought I was going to use. But yeah, there's so many aspects. It's like training. You're just like, whoa, I could go over the dot product. I could go over the cross product. And I didn't even do the half of it, because I could get all these terms, angles, magnitudes, by just using the cross product. Because I could, instead of doing f dotted with this, I could have done f cross this. I get a vector that goes into no man's land, and we can show that. So if I have this perpendicular, and then I have this f, and I do f cross this, hey, I get a vector that way. Well, cool, that seems totally useless, but guess what? The magnitude of that cross product of f crossed with a unit vector is the sine component. So that's really wild, where the dot product, this force vector dotted with a unit vector, gives me that component. Taking this cross that, yeah, I get a vector that way. It seems totally useless. It'll have three components, an I and j and a k, but the magnitude of this is related to, it's that. That's the magnitude. So I could do this whole problem using cross products, and so hell yeah. So I went over the simplest way to get to the answer. Definitely spent way too long kind of explaining stuff, but I mean, I'm literally explaining it for myself, so the next time, yeah, I think you want to learn things, I mean, have a knowledge from like that deeper level. Like, and you know, I mean, you'll see me in future videos, instead of just saying the magnitude of a vector is the thing squared, it's like it's not complicated where that comes from, but damn, it's just a little bit of a proof. So let's do it. You know what I mean? That's why I said it. All right, hell yeah. So let's try to do that on this force. I'm going to go over 2, over 6, and then up 5. Okay, hell yeah. So why can we just do 20 squared plus 30 squared plus 50 squared? Well, you have to do a shadow component. You know what I mean? We know Pythagorean's theorem. That's all we're given. You know what I mean? We just know that, and then you know, there's plenty of proofs out there that a squared plus b squared is equal to c squared. I mean, that's the issue with math, is like proofs have to come from other proofs, you know what I mean? And so you just stack them on top of each other. It's turtles all the way down. But at least, you know, that's where it gets esoteric of just like, what's a number? You know what I mean? You still have to say that, hey, all the numbers are evenly spaced, and they don't mean anything until we put a meaning on them. But if you do put a meaning on it, then every other number is going to be evenly spaced. Cool. Unless you use functions that you know, that obviously manipulate that spacing or that outcome. Anyway, but hell yeah. So we know Pythagorean's theorem. So the take-home point is you always need a shadow component. Like, there's your shadow component. Like, sure, we have this direction, this direction, this direction. And at the end of the day, we're going to square 20, 30, and 50. But how did we get there and take the square root of that? Well, this is still 50. But this right here is going to be the Pythagorean's theorem. It's going to be 20 squared plus 30 squared, square root. So that is that term. Cool. So now what's the hypotenuse here? That's literally what we're trying to find. So it's only a two-step process, but I swear, like, even for me, it seems like any problem you can get stumped on, tricked on, and it can take you all night to, like, figure out where the hell you're going wrong. But hell yeah, so this is a squared plus b squared is equal to that. So cool, we're going to square that. That just becomes 20 squared plus 30 squared. And then we're going to square this 50. So we're going to get 50 squared. So sorry for putting squares on these. It's you know what I mean. So let's talk through that one more time. I want to find the magnitude of this. I know it's got components 20, 30, 50. Always do a shadow hypotenuse. You know what I mean? Cool. So it's just a shadow hypotenuse. And you got to find that shadow hypotenuse. That's 20 squared plus 30 squared, square root that. That's that term. And then we have two parts of a right triangle. So this becomes the A term. This becomes the B term. So we have this squared plus 50 squared. Square root that is equal to RC. So hell yeah. All right. So we are thoroughly done with this problem. And I don't think it was that bad. I think this saved the day. You know, the fact that we have something welded, it's cool. It's got some cool colors. I don't know. You know what I mean? I think I'm done with this video. I don't know if I'm actually going to, probably after I did that cool explanation. It seemed like I was on a roll. But now we just go down a rabbit hole. So I might try to put a cleaner cut together right after the explanation. Try to make a juicy video. Anyway, thanks for joining me on this. And this was way cool. I'm going to do more of these because this literally, I got the hang of it. It's not easy welding thin metal. And I just had a bunch of this just really bendable thin metal. It's less than coat hanger. And man, I threw away all my coat hanger. You know how you just like hoard stuff and then you throw stuff away? Well, I threw it away like 5 years ago, but now I wish I didn't throw all those metal coat hangers away because it's really difficult to find metal coat hangers. Alright, so thanks for joining me on this one, and guess what? That's a video.